All right, welcome everybody to the first instance of the Quantum Science Seminar, where we would like to do something about the fact that there will be no major conferences this summer, or they'll all be significantly delayed. And what we would like to do is bring you the same kind of talks that you would have seen at a major conference such as ICAP, where there are expert speakers who introduce their subject of research to a broad audience. But also talk about their latest and greatest results. And I would like to raise the attention to a similar seminar that was set up by our American colleagues, Adam Kaufman, Monica Schleier-Smith, and Shimon Kolkowitz, which happens every Friday at 9 p.m. European time. You should certainly check that out. It's on amo-seminar.com. where there's already 2 talks available that you can also stream on YouTube. So one administrative thing, because we're going streaming via YouTube live, you will have to submit your questions through email. You just write an email with your question to quantumscienceseminar@gmail.com, or you could also type it into the YouTube live stream. And what we will do, we will take a break sort of halfway through the talk and answer the first questions that arise. And then at the end, we'll do another question session. Please also note that the YouTube live stream has a time delay of about 20 to 30 seconds. And with that, I'd like to hand over to Christian Groß.
Yeah, hello everyone. Also from my side. So I want to introduce our first very famous, very well-known speaker, Ignacio Cirac, that we are very happy to have him with us today. And well, Ignacio is director of the theory division at the Max-Planck-Institute for Quantum Optics in Garching, Germany. His group works very broadly in many directions in the fields of maybe most prominent quantum optics, quantum information, and quantum many-body physics, where he made an outstanding list of seminal contributions. Just to, I think I just checked out the publication list, and just to list the 3 topmost cited papers, that's the Bose-Hubbard model theory in an optical lattice. It's of course the Cirac-Solar gate for quantum information with ions, which actually has his name. And then it's also a famous, highly cited proposal on quantum communication based on atomic ensembles as repeaters. What I found actually most outstanding is actually the list. His list of postdocs and students basically lists now 48 postdocs / students that are by now professor in the world in some form. It's hard to overcome that, I guess. Just to go through prices, that's a bit much to go through all. I counted 21 of them. Just to list 2, that's the Wolf Prize in Physics in 2013 and the Max-Planck Medal of the German Physical Society in 2018. And I think the only thing to say before giving the word to Ignacio is regarding the questions. Ignacio will make a little break, roughly 1/3 in his talk, where you have a chance to put to pose some questions to the first half of the talk. Okay, Ignacio, the stage is yours.
Okay, thank you very much, Christian, for this very kind introduction, and thanks also to Thomas and to Sebastian for organizing the seminar and having me as a speaker. So I hope that you can hear me and maybe you can see me. So can we check if you can see me? So is it okay? Okay, very good. Thank you.
Yes.
Okay, perfect. Okay, great. So well, it's an experiment today because I think this is the first seminar. So maybe some things are going wrong. Let's see. But if something was wrong, so I apologize for that. I'm going to give a kind of a relatively general talk about quantum simulation with physical systems, and it's useful that it has as a goal to simulate quantum chemistry problems. And that's some work that we have done together with Javier Arguello, who is now at ICFO doing his PhD, Alejandro González Tudela, and Tao Xi. These were two of the postdocs that Christian just mentioned. They have now positions in Madrid and China, respectively, and Peter Zoller, who is a long-standing collaborator, and we have done many work together on quantum simulation and many other things. Okay, so let me start with something that probably you know, is that physical problems, quantum problems, when you have many particles, like what we call many-body systems, are very difficult to describe using computers, using classical computers. And the reason is that the Hilbert space grows exponentially with the number of particles, with the volume of the system, and this entails an exponential use of resources, of requirements. You want to simulate them both in time and in memory in your computers. And there are several alternatives to that. So probably you're familiar with quantum computers. So quantum computers can in principle also be used to simulate those systems and overcome some of these exponential scalings. Another very attractive alternative is to use analog quantum simulators. And so these ideas are like a quantum, like an analog quantum computer, in which you may not have control over all parameters of your system, but you can tune your physical system, a different physical system, such that the behavior of the particles of this different physical system, the quantum simulator, emulate the physics that you want to describe. So for example, you have a problem in condensed matter physics or in high energy physics. This is described typically by a Hamiltonian, a many-body Hamiltonians. Then you take another physical system, for example, atoms in optical lattices is a system that people can control in the labs, and now tuning the laser parameters, tuning the electric and external magnetic fields, then this system behaves according to the Hamiltonian that you want to describe. And therefore, you can do your experiment with your physical system and make predictions about the other system in condensed matter or in high energy physics. So that's something that is very well established. So I think that there are many experiments and theory just describing how to do this mapping, so how to map problems in these two fields of physics to cold atoms in optical lattice and some other quantum simulators. And so what I want to do here is to enlarge a little bit the range of possibilities of these quantum simulators based on cold atoms in optical lattices by now showing how you could simulate chemical problems, so like the structure of molecules. And as I want to see is just, this will not be simply just a translation of what has been done in condensed matter and high energy physics to chemistry, but there are new elements. And this poses some theoretical challenges and especially very experimental challenges. But I mean, the goal of this talk and the work that we are doing is to try to convince experimentally such that they start doing activities in this direction of quantum chemistry with cold atoms in optical lattice. And so I will spend quite a while talking about quantum chemistry. Maybe some of the audience is familiar with quantum chemistry. I will assume that you're not, and therefore this is what I want to explain. So why does it make sense to build quantum simulators for quantum chemistry? And let me start with something that is very standard in quantum chemistry. So typically you have a molecule, that the one that I'm showing here, and this you would like to know properties, physical properties or chemical properties of this molecule. So for example, you would like to know, given the number of atoms of one kind, an atom of the other kind, and atoms of some other kind, what is the structure, the equilibrium structure? So somebody tells you that you have C20, H22 on O23, and you would like to know, so what is the physical structure? And once you have the physical structure, so what is the geometry of the system? So how the atoms accommodate together, then maybe you want to know what are the electronic properties, the excitation, reactions, etc., etc. And the way that you can do that is, or describe that, is just first thing, the first approximation that you do is what is called Born-Oppenheimer approximation, in which what you do is that you fix the position of the nuclei and then solve the electronic problem for this position of the nuclei. So that's what is written here. You write a Hamiltonian, which now, since the nuclei are supposed to have an infinite mass, they are fixed. So this means they will give some energy which will be just a number. This is the interaction between the nuclei themselves. And then there is a term in your Hamiltonian which describes the motion of your electrons and also the interaction of the electrons with the nuclei. So this is the Coulomb interaction that depends on the position of the nuclei and the position of the electron. And therefore, and then you also have another term, which is the Coulomb interaction among the electrons. So again, what you do is that you fix this position of the nuclei. And for this fixed position of the nuclei, you solve the Schrödinger equation, you find the ground state energy. Then you change the position of the nuclei. Then you find the ground state energy. And so at the end, what you compute is this function here, which is the energy as a function of the position. And once you have the energy for the different positions, then you can write what is the nuclear problem. So now you write the Schrödinger equation for the nuclei, in which the nuclei now can move. And they're now submitted, or they are feeling now a potential, which is the one that you just solved before. That's the one created by the electrons plus the nuclear interactions. And then you can maybe solve this classically or quantumly or some other approximations, and therefore you can describe the whole system by using that. So let me just give you the simplest example. You have a 2-atom molecule. That is what is represented here. You have the nuclei and the electrons, 2 electrons. So this would be a hydrogen molecule. So you fix the position of the nuclei, you put them like with infinite mass, and then you find the ground state energy for a certain distance, and you plot the energy as a function of the distance, and for example, this point. Then you just move them a little bit away from each other, and then you compute the ground state energy, and then for this other distance, then you plot the ground state energy, and at the end, you can obtain this, what is called the molecular potential. And once you have this molecular potential, you have computed that, then you can study the physics of the system. So for example, you can study vibration. So this would be, now here you will see that there are energy levels here. This would be the vibration level, rotations of the molecule. You can study also dissociation. So here, when the energy is above the dissociation energy, you can study also the dynamics of electrons, etc., etc. But that's the typical approximation that people in quantum chemistry do. First, fix the position of the nuclei and solve the electronic problem. And once you have done that, then you can talk about the physics of the motion of the nuclei, for example. Okay, so the next step, once you have to solve this Schrödinger equation for the electrons. That's the difficult part. And so for that, the first thing that you do is that you find some single electron wave functions. You want to express your Hamiltonian in terms of some wave functions. So what you start is just given the positions of your nuclei, then you write some wave functions, some single electron wave functions for each of them. For example, you could take just the wave functions of the electron, of the hydrogen. And so this would be like, the S state, or N equal, say 1 is equal something, or L equal S, etc., etc. So these would be the different wave functions for electrons for each of the atoms. Maybe you do it a little bit better. You modify them and you put some variational parameters, or maybe you do Hartree-Fock. And with that, at the end, you come up with single electron wave functions. And once you have computed these orbitals, then you write your wave function for all the electrons in terms of these orbitals. You write the wave function of the many electrons that you have as a linear combination of all these orbitals, one particle in each orbital, and you antisymmetrize because we have fermions. Of course, we know very well that this antisymmetrization is very nasty, and it's much better just to use second quantization. So indeed, you use second quantization, and you use second quantization, then you can describe mode operators that create and annihilate particles at orbital j and orbital I here, and you can just project the Hamiltonian in second quantization, and you get what is the Hamiltonian for the electrons, which for many of you will look very familiar because it looks like a Hubbard model. So the electrons can jump between orbitals. That's the first term with some coefficients, and the electrons can, through interactions, change orbitals. That's this term over here. So at the end, the problems in quantum chemistry is reduced into first finding these wave functions, and that's something that can be done very efficiently. Typically, maybe it's a little bit uncontrolled in the sense that you may not choose the right orbitals, and then your problem, of course, will not be correct. And the second part is that then once you have the orbitals, that you can compute the coefficients of your Hamiltonian. Now the question is how to solve this Hamiltonian. And as you see already, this Hamiltonian has many parameters, because this term here with m is the number of orbitals, and it has m to the 4 parameters. And to solve a problem like that, actually, it's very difficult. And so, for example, you want to find what is the ground state of this Hamiltonian, then you want to do it exactly, then you're limited to a few electrons, maybe to 5, 10, 20 electrons at most. And that's why, I mean, this is due to this exponential growth of the computational resources that you will need in order to solve this problem with a classical computer. Maybe you can solve it with some other ways, perturbation theory, coupled cluster method. There are many methods, but somehow one of the most popular ones is this density functional theory. And I want to explain it briefly what this density functional theory is. A way of solving this Hamiltonians, or the electronic Hamiltonian. And the basic idea is that there is a theorem from the 60s or the 50s, which tells you that actually the total energy of electrons and for a given position of the nucleus is a function that depends of the density. It's a functional on the density. This is what is called density functional theory. So in fact, you are able to compute this energy as a function of the density. So you give me some density in space, and this E of m gives you a number. You're able to compute that. Then the only thing that you have to do is to minimize with respect to all possible densities, and this will give you the ground state energy. And actually minimizing, if you have this function, is something that is very simple. It's one particle problem, so you can do it very fast. So the question, and the difficult part, is what is this functional? What is this function of the energy as a function of the density? And you can convince yourself that the kinetic part of the electrons can be written as a function of the density. Also, the interaction with the fixed nuclei is also something that depends on the density of the electron. Also, some exchange terms will be a function of the density. However, the other parts, so the real interaction between the electrons, the Coulomb interaction between two electrons, is a function that you don't know. It's not easy to compute. Actually, one can show that is NP hard, so it's very difficult to compute it. And so what people do in practice is that they guess it. So depending on the problem that they want to solve, then they put here some function. This gives you some E, and then they do the solution, and that's how it's solved. So this is a method that is extremely efficient. So actually, it scales somehow like with the number of orbitals, not to some power. So I don't remember exactly what power, but this very low power can give very accurate results. It's very widely used in chemistry, but the question is, so how to choose the density function, and how do you choose that? And that's an art, because depending on the problem that you want to solve, you have to have a good nose to see what is the function that you have to put. And sometimes you put a function, it works, sometimes it doesn't work. And actually, in order to use this theory, then it's very important to have a way of benchmarking. And so to see what is the function that you have to choose, depending on the kind of atoms that you are going to have. And that's not so simple to benchmark. So people do it with experiments, but experiments are room temperature, things like that. So it's more dirty. So that's something that is difficult in chemistry. And also you cannot design in order to benchmark all possibilities. And so that's one of the key points of my talk, that is benchmarking. It's an important issue in chemistry, not only to solve problems, but also to benchmark theoretical methods like this widely used density functional, or one that would use tensor networks, or a coupled cluster, or perturbation series, etc., etc. I think it's very much required to have a good way of benchmarking. Now, you could use also a quantum computer to solve this problem. That's actually our model. And so at the end, you could just use your quantum computer to find the ground state of your Harvard model. And in fact, there are algorithms to find the ground state of Hamiltonians, but all the quantum algorithms that exist for quantum computers require an exponential time with the number of orbitals or the number of electrons. So even a quantum computer for a general Hamiltonian like that requires an exponential time. However, we know in practice that there are some other algorithms that maybe adiabatic preparation or variational that probably will work very well in practice. And so for that, it would also be good to have benchmarking, so that one could benchmark some of these methods for these practical algorithms. So summarizing this very long introduction and motivation of the problem, so I say that in quantum chemistry, the most difficult part of the problem is to solve the electronic problem. You fix the position of the nuclei, and then you want to find what is the ground state of the electronic system. That at the end is a Hubbard Hamiltonian, and you can try now to use it. And well, the first thing is that this Hamiltonian already makes an assumption, is that you have selected the right orbitals, and maybe this, I mean, this doesn't have to be true in general, so maybe you just chose some ones which will not be accurate enough to describe your system. On the other hand, you want to use now a classical computer to find the ground state energy of this Hamiltonian. Then exact methods are hard, so you're very limited in sizes. And you want to use approximate methods like this density functional theory, then it's probably very useful to have a way of benchmarking the methods. And for quantum computers, also with full quantum computer, well, first of all, they are very hard to build, as we know, and you want to run an algorithm like the algorithms that have been presented, and probably it's even hard there as well. However, with these first generations of prototype for quantum computers, there are approximate methods that are going to be used in order to solve these problems, and it would be good also to have a way of benchmarking. And so coming back to my first transparency, as I told you before, in quantum simulation, basically what you want to do is to solve many-body problems now using a simulator, in this case called atoms in optical lattice. And so that's what I want to do here. So to show how chemistry problems could use a quantum simulator to solve some of them, or some particular class of them. So I will show later on, and this could be used in order to benchmark your numerical methods. And I have to say that probably this, I mean, at least for me, that's also probably the most important application of simulator, not only in chemistry, but also in condensed matter in higher energy physics. It's not only that you're going to solve problems with them, like the phase diagram of the Hubbard model, something like that, but this would allow to benchmark theoretical methods, tensor network methods, or Monte Carlo, whatever, many methods that exist that cannot be benchmarked. And if you had experiments, then I think that theorists and experimentalists could work hand in hand in order to get a better understanding and better descriptions of many body systems that at the moment we don't have. So I think that it's a good time to stop for questions, and because then I will go to quantum chemistry and describe how you can do that with cold atoms in optical lattices.
So Ignacio,
yep.
There has been one chemistry-related question from Didi Leibfried at NIST,
yep.
And he's asking, when does the Born-Oppenheimer break down, and is that ever a problem for a real molecule?
Well, I'm not an expert on chemistry. I think that the corrections of Born-Oppenheimer go like the ratio of masses of the electron with nuclei. So that's a factor 1/1000 or 1/2000 or something like that. So typically they're small, but we know that there are some particular problems where the Born-Oppenheimer approximation misses some interesting physics. I mean, I think that they're related to Berry phases and things like that. You can miss these questions. So indeed, I mean, most of the problems I think that are, it's enough to do Born-Oppenheimer approximation, but there are some particular problems where Born-Oppenheimer cannot be done. And I will have a comment about that at the end of my talk, so how to go beyond Born-Oppenheimer approximation and to do simulations where the motion of the nuclei could also be simulated.
Okay, and there has been a second question by Raman Chudari, and this one, the first one is, what does the density of electrons physically mean? And following up on that, how is the second quantization easier than the anti-symmetrization?
Okay, well, that's the density of the electron is just the number of electrons per unit volume. It's just the density, so how many electrons are at each position of the space. It's the normal density of electrons. And the second, well, I mean, you can, I mean, everything is equivalent. You can work with second quantization of first quantization, but the second quantization is very useful if you want to, for example, use a quantum computer. So you have discretized orbitals, because you can transform this into qubits, for example. And also the anti-symmetrization operator, it's a very nasty one because it doesn't keep normalization. So you have to normalize your state, and it's nasty. Of course, you can always do it, but it's the same thing as if you want to solve your integrals, yes or no, doing sums, or you can do it analytically. You probably do it analytically, not numerically, because it's much more useful. Okay, so then I'll continue. So I'm going to talk about this work, analog quantum chemistry. That's a first proposal that we wrote in order to show how you could use cold atoms in optical lattices for analog simulation of quantum chemistry problems. And so let me go back to these atoms in optical lattices, like explaining a little bit more detail. So atoms in optical lattices is a physical system where neutral atoms are trapped by light forces. So you have some light field that propagates in different directions, and then because of interference, there is some pattern that is typically a periodic pattern, some cosine in the 3 directions, in the 3 special dimensions, and the atoms now feel the intensity of the laser at each point as if it was some potential energy, changes the potential energy. So at the end, the atoms are, like what this drawing is showing, move in this potential, and so they typically are at the bottom of the potential, and they can tunnel from one place to another one. And in this way, they can move. This is very reminiscent in the way of how electrons move in solids. And this is why these cold atoms in optical lattice was first thought to simulate problems in condensed matter physics related to the motion of electrons in solids, where the electrons can hop from one ion to another ion. And when electrons meet at one point, then they interact with each other. And mathematically, this is described by Hubbard models, very similar to the one that I wrote for quantum chemistry, in which your Hamiltonian has a part which describes the hopping of the atom. So one atom disappears from position n and hops to some position nearest neighbor site, for example, here. And also when 2 atoms meet at the site, for example, then they will have some interaction, and this is the interaction energy that may depend on the spin and some other properties, but that's the same Hamiltonian that describes the motion of electrons, let's say, in solid, this kind of toy Hamiltonian that does it, describes from first principles the motion of cold atoms in optical lattices. Now, as I mentioned before, that's very similar to the Hamiltonian that we want to simulate. So in principle, one would think, well, let's tune just the parameters of our system in such a way that we solve this Hamiltonian, so that we have exactly this V, I, J, K, L. However, this is not as simple. This is not actually possible. And the reason is because, so typically here you see that the Hamiltonian that you have depends on the density. So it has a density-density interaction, whereas the Hamiltonian in quantum chemistry does not depend on the density. So particles in orbital I and J can interact and go to 2 different orbitals, and that's very different from what happens with cold atoms in optical lattices. And also the interactions here may be non-local. So one atom from an orbital that is here can jump to some other atom or can interact with some other one that is there and get into an orbital that is here and another orbital that is there. So many non-local things can happen. So that's why it's not straightforward how to simulate using cold atoms in optical lattice quantum chemistry problems, because in cold atoms, the interactions are typically very local, and in quantum chemistry, interactions are very non-local. In fact, the Coulomb interaction is very non-local. So what we propose actually is to use cold atoms in optical lattice, but in a different way. So this would be more like a very analog simulation in which you will have some fermionic atoms that move in the optical lattice. It would be these ones here that can hop. And on the other hand, there will be some regions where you have some laser light that would create some potential for these atoms. And this would simulate the effect of the nuclear interaction between, or the interaction between nuclei that is at a fixed position and the electron. And on the other hand, you need some electron interaction, and this will be done by using some other atom, a boson, that will mediate the interactions between these two. So let me show it in this Hamiltonian. So I told you that this is the Born-Oppenheimer Hamiltonian. This part doesn't matter because it's classical. This describes the motion of the electron. So this here will be the hopping of this fermionic atom, from one place to the other one. On the other hand, the term that describes the interaction of the electron with the nuclei will be represented here by this external potential created with laser light that will attract these atoms towards the potential. And this interaction between the electrons will, actually, in order, because this has to be long range and these atoms are neutral, they don't have interactions that are long range. So what we will do is to simulate or emulate what nature does. So if you look at the origin of Coulomb interaction, the 2 electrons interact with a force that goes like 1/r squared, or potential that goes like 1/r. The reason in quantum electrodynamics is because they exchange photons, because they exchange bosons, these gauge bosons. So here the idea is to replace the photons by some bosonic atom, and this bosonic atom is the one that is going to mediate the interaction. And as I will show you, it is possible that this atom mediates an interaction that goes like 1/r, like it's required for these quantum chemistry simulations. Okay, so some comments before going ahead and going into the details. So first, that's very different from the proposals and experiments on quantum simulations for condensed matter physics and high energy physics. The first difference is that, as I mentioned, in quantum chemistry, you need long range interactions and interactions that decay like 1/r or something like that. And so this makes that the typical setups of cold atoms in optical lattice, you cannot use them, the interaction among themselves directly. You have to use this other boson to mediate interactions in order to get these effective long range interactions. The second, that is an important difference as well, is that so in cold atom in optical lattice for the simulation of condensed matter or high energy physics systems, you have many atoms. Okay, so you have the density is of the order of 1, so there is 1 atom per site. It's an interesting regime. However, here you have very few atoms. So you will have, for example, you want to simulate a molecule that has 2 electrons, you will have 2 atoms and maybe another one that is mediating interaction, or I will show maybe a couple of them that are mediating interaction. So these is a different realm for cold atoms in optical lattices, in which instead of working with many atoms at the same time, you will have very few depending on the electrons that you want to simulate. Another difference from standard quantum chemistry is that here we are not using orbitals. So here, I mean, a space is a space. So if you want, one could say that what we are using are spatial orbitals. So what we have is that each of these lattice sites is like a spatial orbital, and the atoms just move in these orbitals. And so it's not typical orbitals of hydrogen atoms what we're talking, but just the spatial, just natural orbitals. One other difference here is that if we want to really simulate quantum chemistry, then at the end you have to go to the continuum limit. So you will have to make your system sufficiently large and such that all the wave functions are kind of smooth with respect to your lattice. And in this way you recover the continuum limit. And that's part of the difficult, I mean, there's a difficult theoretical part for the description of the system. And I will not talk about that, but that's what requires more, let's say, more theoretical techniques. And also is what Didi was asking. So in principle, you could also include the dynamics of the nuclei. I will not talk about that, but in principle, instead of having this external potential created by lasers, this could be some other kind of atoms that also interact among themselves and with electrons, just also sharing some other bosons. And this, they could move as well, and this would be even more complicated, but this could even include the dynamics of the nuclei. Okay, so I told you what is the basic idea. And so the main questions now, how to do these things in practice is, first of all, so how you can create an external Coulomb potential, so some potential maybe with laser light coming from outside in such a way that the fermions feel an attraction to that potential, and this attraction depends on the distance, like 1/r. The most difficult part is how to get an electron-electron Coulomb interaction, some interaction between the electrons that decays like 1/r. And then there are some other questions about the discretization and so on that I will not talk here. Then there are some technical questions. So now it's which kind of atoms, which species, or how to prepare, how to measure disadvantages, the coherence, final temperature. So we have analyzed some of these things, and I will not present them here, but well, I'm telling you from the sketch that this is an extremely difficult experiment. So later on, I will tell you how to simplify the experiment, but the way in which I'm presenting it here, it's not only challenging, but it requires an effort that goes well beyond the current technological possibilities. Okay, so first is how to engineer this external Coulomb potential. And the idea can be taken from the group of Antoine Brouets, in which they were able to have atoms in optical lattice and with some holographic membranes, they were able to design potential for the atom. So what we have done is that we have taken these kind of membranes and see whether you could create with these membranes a 1/r potential just by putting the different phases and so on in the membranes. And we have seen that actually this is possible and this is very realistic. So you have something like a 50 by 50 by 50 lattice, and you have one of these membranes, even if it's in 2 dimensions, this membrane was in 2 dimensions, then you can focus and have a potential that looks very much like 1/r at different positions. So I think that's a technical, problem, but for the theoretical point of view, with these membranes, this could be done. The second part is about the electron-electron interaction, and this is, I want to spend more time talking about that, but that's the more fundamental part. And so for that, what I'll do is that go back to some papers that we wrote together with Inés de Vega and Diego Porras and Carlos Navarrete 10 years ago. And at that time, we were interested in how to simulate quantum optics with cold atoms in optical lattice. So how to simulate things like superradiance or subradiance or collective effects or single particle effects or Purcell factors or Purcell effects with cold atoms in optical lattices. And the idea is sketched here is that imagine that you have now you have atoms in optical lattices, and these atoms have 2 internal levels, the level B and the level A, and they are connected by a Raman transition. So you have 2 lasers that can transfer atoms from state B to A. And on the other hand, imagine that now you use different lasers for the different internal states. So you have what is called state-dependent potentials. So you are in the state B, then you feel a periodic potential like the ones that you had before in atoms in optical lattices. This is one here. Whereas if you are in the external level A, then you feel some more confined potential like the ones that is here. Okay, so if you have the situation, then what can happen is that you have an atom in the internal state B here, and then because of the Raman transition, then they can hop to the level B, like this one here, maybe somewhere here. Now it can move in this potential and maybe get another time the laser back and go back to this level here. So this would correspond to a hopping from here to here. And now if you use the following description, if you say that if there is an atom here, you call the state E of this atom. But if there is no atom, you call it G, then you see that what happens is that you have initially state E, and then when the atom disappeared, you went to the state G. Now, this atom appeared here. So now you have an atom that is moving here. And this other site that was originally empty, so was in level G, now when it absorbs the atom, then it's in level E. So what you see is what happened is like a flip-flop interaction. You have, in this language, an atom in the excited state that went to the ground, or a particle in the ground state, in excited state that go to the ground state. And here, when it appears here, it went from the ground state to the excited state. So here, I mean, these particles are not ground and excited state, it's just the language. So I'm saying that the presence of a particle at a potential is like having one excitation, and the absence of this particle is like having no excitation at this particular level. And you have the situation, then what you see is that you can have that your 2-level system, this effective 2-level system, can flip from one excited state to the ground state and another one from excited state to the ground state. And actually this emulates very well what happens in electrodynamics, that you can have an atom in the excited state that go to the ground state that emits a photon. The photon would be now the atom here that can move, and this is absorbed by another atom that is here. And that's actually what we propose in this paper. And now, if you are familiar with quantum optics, then you can see that now there is an effective dipole-dipole interaction, that this process of going back and forth, if you do it right, then provides a flip-flop term. That's kind of a dipole-dipole interaction. And in particular, if you have some Raman detuning in such a way that this is off resonant, as is represented here, then you can look at the dispersion relation. And if you have your atoms in level A, then since you have periodic potential, then they will be described by this dispersion relation. And you put your frequency of resonance like it's here, then you see that in principle you cannot make transitions because you're not resonant, so you cannot come from here to here. But however, what you can do is virtual transitions. So in principle, you can come from here to here virtually, and then back from here to here. That's what happens typically in quantum optics. And that is what's represented down there. So you can have an atom initially in this state A at some particular point, and then can take photons, can go virtually to one of these states here, and then go back. And this is the flip-flop interaction that I mentioned before, how it can go from one place to another. And if you want to compute what is the effective Rabi frequency for this process from going from here to here. Then we know that it's like the product of the Rabi frequencies divided by the detuning. So you'll take the Rabi frequencies divided by the detuning. But actually, since you have many modes here, you have all these modes, then you have to sum with respect to every mode. So you can come from the initial state to the final state over many modes. So you have to add, and this is this integral that is here. And so actually, this is the formula, like the formula for the effective interaction. And this is because you are taking, I mean, these are plane waves. And so this is where you get this e to the equity. So what I'm saying is that at the end, having atoms in optical lattice, then you can consider, and I mean, just hopping from one place to another, from in level A, from one place to another via virtual transitions in B, gives rise to some kind of spin Hamiltonian. And this spin Hamiltonian is described by a hopping term, which is this this formula, is given by this formula here. And now, I mean, you can do this integral, but you can see already, looking at the dimensions of this integral, you see that you have a k to the cube in 3 dimensions and a k squared in the denominator. So the dimensions of that goes like k. And the only parameter here, which has units of length, is this d. So this has to go like 1 over d. So you see, just doing dimensional analysis, that this Rabi flopping will depend on distance and goes like Coulomb interaction, like 1 over the distance. And so, in fact, when you do it properly, then you will find that the effective Hamiltonian in this new language, in which one of the part excitation can hop from one place to another one, is this term here. This, I mean, develops the flop, or the kind of the equivalent potential for this to happen, just the case in like 1 over r, the appropriate limits. And so that's what we want to use now. We want to use this effect in order to get the effective interactions between the electrons. And so we go back to the problem that we had before. Now we have these electrons that are here. And now you can try to say, well, let's have the boson. And if this boson interacts with one electron, it's originally here, then it will make interaction. But the problem that you will face is that if it's originally here, then it will go forth and then back. So this will be actually a high ordering perturbation theory. So you will not get 1 over r, but you will get a 1 over r squared. So that's why this directly doesn't give you the whole Hamiltonian that you want. And so you have to use a trick. And this trick actually creates a large or a huge experimental difficulty in order to do that. And so I don't want to enter into the details of this trick. But the basic idea is that you look at this Hamiltonian and you have 2 of these 2 particles, and you look at what is an eigenstate of this Hamiltonian. Actually, this eigenstate has an energy which now will depend on the distance between the particles. This will be this E of d that will go like 1 over d. So the idea is to prepare this this boson in an eigenstate that follows adiabatically these particles. So in a sense, while these particles move, they just move with them, and therefore the energy that they experience is 1 over d. So actually that's good, but it's not scalable. So one can show that if you have 3 particles, then the eigenstate will not have this property. So you will not have that the 3 electrons, the energy between 3 electrons will be the sum of the corresponding Coulomb interactions. So actually, there's not a way around that. And the idea is to put like a background mode insulator, so to have a set of atoms that are stopped at these particular places, and that they have some internal level. And now the spin of these atoms is the one that plays the role of this excitation that can tunnel. And if you do something like that, then will basically work. But still, you have to stabilize it because the effective interaction is still not quite right. And so for that, you need to put even a cavity to stabilize it. So I don't want to enter into the details, but the experimentalists that are listening to this talk will be by now completely scandalized, and there is a reason for that, is that altogether you want to simulate this 1 over r potential, then you would need to have, like, apart from the 2 fermions, you will have to have a mod with certain internal states and a cavity that is interacting with these bosons that is stabilizing, and this will give rise to this potential. So that's what I'm saying on paper is possible in principle, but requires a combination of technologies that each of them individually are very hard. So it's something to think for the the future. Okay, there are all these technical questions. So what kind of atoms to use that? We were very fortunate to talk to Sebastian Blatt, who told us, about the earth alkali isotopes. And so we just thought, specific schemes of how to do this in practice and how to use the cavity mode and put numbers and so on. We also thought a way of preparing the ground state adiabatically, also of measuring at the end, so how to measure the energy by time of flight, etc., etc. But these are details. In any case, so the summary so far is that, okay, so you want to have a quantum simulation of quantum chemistry that corresponds really to the physics of molecules with the potential that they have in the continuum, etc., etc. This is in principle possible, but it's hard in practice. And so maybe what I want to talk about now is that we wrote recently a paper about a simplified version of that doesn't capture all the details for quantum chemistry. However, it's much more experimentally friendly and can be used in order to benchmark methods like DFT and some other methods. Okay, so the idea is, first of all, to work in lower dimensions, just to work in 2 dimensions, not in 3 dimensions. That is what is represented here. And to what I mentioned before, so to use just a single atom that is accompanying one of these fermions, and through this back and forth interaction, this will give rise to some effective interaction between the electrons. And this interaction will be not one, will not be the Coulomb interaction. But it turns out that if you do it in 2 dimensions, then you compute what is the interaction, and it is 1 over r. Because in 2 dimensions, 1 over r is not the natural Coulomb interaction, as you probably know, it's logarithm of 1 over r. But still, if you would do an experiment with 2 particles and you would use this trick in which there are only the 2 fermions and 1 boson that can hop among them, then this will give rise to kind of a quantum chemistry problem with a Coulomb interaction, but now it will work in 2 dimensions. Another possibility that we have thoroughly investigated is the one that in which of having 1 boson that can hop between the atoms, to have 1 boson accompanying at each of the atoms. These are like the doublons, in which you will have a fermion and a boson now hopping in the lattice. And now the bosons can also hop, interact with the other boson and come back. And this also mediates interaction. However, this is a scalable proposal. However, here the decay now goes exponentially, so it's not it's a very different law. But we have done computations with this model, with this system. So we have now done computations with classical computers, of course, and consider different experimental situations. So one of them would be the simplest one. The simplest one is that you have an external potential, just one, like a nuclear, and one of these fermions. So this would correspond to the hydrogen atom, and in this case, you don't have to engineer any interaction between the electrons, so you don't need any boson. So this would be just one fermion problem. And so we have analyzed in terms of the size of your lattice and the parameters that you have to put there. So how well you will be able to reproduce the hydrogen atom in 2 dimensions. And so, well, I don't want to enter into the details, but here you see for different lattice size. So this is a 40 by 40, 80 by 80, and 200 by 200. So here, this is the tunneling amplitude of the tunneling energy between the fermions. That's the potential energy related to the Coulomb interaction. So this would be the interaction between one side and the next one. So you put an electron next to the center of where you have focused your laser, then this is the energy that it has. And this plays a role in this model of the Bohr radius. So this is like plotting as a function of the Bohr radius. And so this is the exact continuum limit. And then you see that depending on the size of your system, then you can approach the energy for the ground state, for the first excited state, for the second excited state with the right degeneracies, etc., etc. And so this is the error that you make in the continuum as a function also of the same parameters. And you can see that, you get some results. So this would be the next more difficult experiment. This is that the hydrogen-like ion molecule. So you consider now that you have 2 external potentials, so 2 nuclei, but only 1 electron. And so now you can put different distances, this external potential, and then you can now simulate. So what you will have, you have a 40 by 40, an 80 by 80, 200 and 200, and you see that indeed you have, even for the 40 by 40, you have some dissociation potential. So you will see a dissociation potential in that system. And the next thing is what happens now, you have the hydrogen molecule. So you have now the 2 potentials with 2 fermions and one boson that is mediating the interaction. And again, we have done the same computation. First, we have shown that it goes like 1 over r. So that's what is here. It's a function of the distance, as it should be. And then we have also seen that there is some dissociation potential even for a 20 by 20 lattice. So this means that, I mean, if you put more electrons or more fermions and you do this computation, then you could see the physics of molecules, I mean, dissociation by, the things that I was talking about before. And this could benchmark your methods, your DFT methods. You will not use the DFT for the continuum. You can adapt it for the discrete case, and then you can benchmark with this problem that as soon as you have something like 10 or 15 of these fermions, then it will be extremely difficult to solve with any other method. And that's the last one, is also the hydrogen-like molecules of H2, and with the other scheme. And so we also see that for the other scheme, in the one that you have this exponential decay, then you have this kind of dissociation potential as well. So the summary of all that is that indeed with this simpler scheme, then you could have some toy models. These toy models can get have the physics of the chemistry of these molecules, and at the same time, some of these models, as you put more and more particles, are very difficult to solve. So you have an experiment. This could serve as a benchmark, as I mentioned at the beginning, for other methods. Okay, so I'm about to finish now. So just to mention that we thought a little bit of a roadmap now for quantum chemistry. So one can start from something very simple, just to work in one dimension, to use as an external potential, not these holographic methods, but a focused laser, just a single atom and a single or no boson, or a couple of atoms or a single boson. Then you can complicate it going to 2 dimensions maybe, and having two atoms, and maybe the next step would be to use a multi-insulator as we wanted before, and then you can go to 3 dimensions, start using holographic potentials, more than 2 atoms, and at the end put the cavity, and this will leave the full fetch quantum simulation as we propose. So in summary, okay, so the take-home messages of my talk, first of all, is this simulating molecule is very hard, it's very difficult with classical and even with quantum computers. However, and there are some methods, like classical methods, and we hope that also with these NISQ devices, but both methods would benefit very much from benchmarking, and you could benchmark whether the orbital that you select is good, or if the density function operational method is okay. And for that, for this benchmarking, so we propose analog quantum chemistry with atoms in optical lattices. I told you that in principle, a full solution that will fulfill all the properties is possible, but in practice it's very difficult because it requires to put together many technologies that are difficult by themselves. However, we believe that in the first steps in experiments, one could start with toy models and then grow these toy models, and then there will be a position at which these models would be useful in order to benchmark the methods that I mentioned before. So as an outlook, so things that we're looking at the moment, we are also thinking about not using this bosonic atom in order to mediate interaction, but Rydberg atoms, also how to do it with ions or maybe with atomic arrays and photonic crystals. Also with Lieven van der Sippen, we're thinking about how to do these things with electrons in quantum dots. They work directly in the continuum. And as I mentioned before, so to include maybe the later stage, also the nuclear motion. And with that, I would like to finish and thank you for your attention.
Let me clap on behalf of all the Adams for this really great tour through ideas on analog quantum simulations for quantum chemistry. And I know we have a bunch of questions, and I would hand over to Thomas again for posing them.
So Ignacio, there was one question which was based at, like, starting from the back of your presentation by Pavel Pushkin. And he's asking, it seems that the proposed method is about the dynamics of the quantum system in the lattice, meaning the solution of a time-dependent Schrödinger equation for a given initial state. But how is the task, the solution, related to the eigenvector problem that you used in the beginning of the presentation? How are they related to each other?
Okay, so this is a concept general not only for this simulation of quantum chemistry, but in general for quantum simulation. So the first thing, if you want to do quantum simulation, you have to find the ground state of your system, the energy of the ground state, which was the goal of what I was explaining here, the first thing that you will have to do is to see that you can implement the Hamiltonian, that your simulator actually behaves in the way that is described in terms of the Hamiltonian that you want to solve. That's what I was showing here. Once you have that, then you have to prepare the ground state. This I didn't explain it here. So how to prepare the ground state of your system, and that's the same thing what happens with condensed matter simulation or high energy physics simulation. And the typical method of doing that is by adiabatic puzzle. So you start with a configuration in which it's easy to prepare in the experiment. You put maybe the electrons next to the potential, to the nuclear, and switch off the interaction between the electrons. So you just tune the parameters in such a way that this boson does not interact, does not mediate an interaction, and then you start changing it slowly in such a way that you evolve adiabatically to the ground state of your system. This is how you prepare the ground state, and this would be an equilibrium state. And once you have this ground state, what you would like to do is to measure the energy, because this is what we wanted. The energy is a position of the nuclear. So you fix the position of the nuclear, then you measure the energy. And to measure the energy, then you will have to do some time of flight, and so to measure some quantities that I didn't explain here, but there is a method to do that in practice.
Okay, thank you. Then the next question by Yaroslav G. And his question is it possible for some molecules that a finite M of orbitals can't be a sufficient basis for a precise solution for the chemical problem? And if so, for instance, high energy modes conspire towards a finite contribution and so on? Yes,
I think that if they are very high energy, they will not conspire because energy has to be conserved at the end. But what may happen is that your orbitals are not good enough, and this happens in quantum chemistry. You start thinking of some orbitals, and then you make some predictions, and at the end you see that the orbitals that you took are not very relevant. So they don't describe the whole physics of the system, because there are some other modes that even they will contribute to the low energy that are not included. Because the way that you find these orbitals is just by Hartree-Fock or some methods. These are approximate methods. This is not exact. These are not. It's not the. The fact that you optimize some method like Hartree-Fock doesn't mean that the description that you will have at the end with all the interactions will be based on these orbitals will be correct. So that's something that it would be good to benchmark. So indeed, it can happen that your orbital is not enough and that you will have to take some other orbitals.
Okay, this brings us to the last question. This has been raised by both Berat Lien and Aaron Rodriguez Jimenez, and they both would like to know, could you please explain a bit further what do you mean by benchmarking, which you have repeated on your slides? Do you mean analyzing the time and spatial complexity of the algorithms depending on the choice of functional function Fn?
No. By benchmarking, what I mean is that, for example, let me be concrete. Imagine that you have a problem that corresponds to 10 electrons and some nuclei, and you want to solve it with DFT, with one of the methods. Then at the end, your computer will output some energy. And so you don't know whether this energy is correct or not correct, because the only way of checking if it's correct or it's not correct is to solve the problem exactly, but you cannot solve it exactly. And depending on the functional that you put, then you will get different results. So how do you know which is the right energy? So you have a quantum simulator, then you could prepare the experiment, implement this Hamiltonian, measure the energy, and then check that this energy is the one corresponding to DFT or not, or that one of these. So this is what I mean benchmarking, that you put a problem, take a problem, solve it with a classical method or what method, you do it with a quantum simulator and check when it's right and when it's not right. And this will allow you to perfection your method, to improve your method, and therefore to develop a better method to describe these systems.
Thank you. I'll leave it at that.
Okay, thank you, Thomas.
Okay, many thanks again, Ignacio, for this talk. It was, it's hard to imagine a better start for the seminar. And let me clap again on behalf of all the others and say again, thank you. And now I hand over to Sebastian. He has something to say for the next seminar.
Hi, yeah, just from me really quick to remind you that this seminar will happen every week. And next week, we are excited to have Roy Ozeri from Weizmann, who will talk about ion trap quantum computing. And if you want to get notified about the newest seminars, about the schedule, you should subscribe to our email list and you should subscribe to our Google Calendar. Well, thank you for your interest, and we hope to see you again next week, same time, same place. Bye then.